bit about Cloudmesh and why Cloudmesh is important for example, this particular class. Well, when we are looking at big data, we do actually need a cyber infrastructure stack that supports the research that we will be conducting on big data. We have a lot of software services that are being running to analyze the data. We have platforms that make the development of tools to analyze the data easier. We have infrastructure as a service on which these platforms are being hosted, and the infrastructure as a service frameworks typically are on top of bare metal as a service services. Now, examples for some of these things are, for example, Mahout as a software as a service, Hadoop as a platform, OpenStack as an infrastructure, and Cobbler as a bare metal as a service. These are just examples. You can pick any other number of examples, but there are many of them. And we observe that there are many tools there, and the installation of these tools is fairly complex at times. As we said, we have hundreds of offerings that the users may choose from. Often it's unclear which offerings are most suitable for the particular problem. Sometimes we may actually not even care which one it is, as long as we can use the software service that is being offered. And the other problem that we see is that many infrastructure as a service frameworks are existent, and we would like to use all of them because maybe our problem is so big that we use multiple distributed resources. Now, one of the things that we have asked ourselves is what should be becoming part of Cloudmesh. So we haven't Cloudmesh developed in isolation. We have developed this originally as part of FutureGrid, where a lot of users were registered and a lot of projects were being conducted. Many users were in the United States, but we have actually an international user community in FutureGrid. And this project is continued as part of Future Systems at Indiana University also. When we analyze the projects, what we simply have done is we have simply taken the project application descriptions and identified several of the keywords that are sticking out. And so we find cloud computing and MapReduce and data and those kind of things, bioinformatics and distributed and OpenStack and clouds and Hadoop. So we can already see from this particular set of keywords mapped into a word cloud that the analysis and the use of these infrastructures spawns the entire stack. It's not just on the infrastructure side, this is the entire stack. Now, we have also asked the users to provide keywords, and the same trend can be verified here. Here we can actually see some of the interesting keywords, like for example MapReduce, that are working on this, or a course even being taught in big data or infrastructure as a service. We also have analyzed what the service requests are for each one of these projects, and we see a really interesting trend. Initially, when we started with the project, Nimbus and Eucalyptus were quite prevalent, and a lot of users wanted to use these particular infrastructures. However, we have seen a reversal in the trend where these infrastructures became less popular and have been becoming replaced by OpenStack. However, we have still a very significant number of users in the other area. However, as FutureGrid stops, we will be focusing naturally on our OpenStack activities. Additionally, we also see that the high-performance computing activities are still requested, so there's a quite big demand. Why is that the case? Well, high-performance computing naturally delivers a performance advantage over some of the virtualization software that may exist because we have exclusive access to the bare metal hardware in high-performance computers. And Hadoop, for example, performs very well on HPC. We also observe how many users are in these projects. We see naturally a lot of users have one uh, user only, but then we also see a lot of users that have multiple users. This also means that the software, and especially the infrastructure as a service frameworks that we need to be choosing, must support multi-user environments. That is, we have projects in which multiple members are part of the same project, and the accounting for that particular project is being done with multiple users. So it's not sufficient to just give a single user an account and the single user can actually do these projects. Similar to Unix groups, there must be a group mechanism that allows project groups to be created. Together, these requirements have been put into a new software system. The software, we use the term software-defined distributed system as a service, encompasses all of the services that we have listed previously, and allows us to define a distributed system via software tool and offer it as a service to the user. This means that a user can deploy a software stack with the help of Cloudmesh. One of the other things that we observe is that there are many public clouds available. Amazon, Microsoft, Google, Rackspace, HP, and many, many others. We also have private clouds, maybe the cloud that you have access to in your university, or the cloud that you are managing yourself. We have high-performance computing batch services, or sometimes also now accessible through cloud services, which are really bare metal provisioned resources that allow you, for example, access through a system that is being maintained by a system administrator. Now the question is natural, is because some of our problems may be so big that not a single cloud maybe satisfy our needs, or the cost of using one cloud over the other cloud may be better, or we would like to be independent from the offerings from one of the vendors. Thus, the question is natural, can we leverage all of them? One of the other things that we observed over the couple of years is that the technology has frequently changed. Now, you don't want to adapt every single time a new platform comes out, your software. You would really want to be having a stable software. Cloudmesh has, over the last 2 years, provided some really stable services and an API that hasn't actually changed. So it was possible to write a certain stable applications. So we can use software-defined infrastructure and software-defined applications while leveraging this infrastructure that is available as part of public clouds, private clouds, and HPC clouds. Now, to accomplish this, we need to have a Cloudmesh architecture defined that is tightly integrated with the infrastructure and delivers a toolkit. This toolkit must be able to encompass virtualized and bare metal infrastructure. It must be integrating network, applications, systems, platforms, and naturally the underlying software defined services that build the distributed system. Well, this system we call actually Cloudmesh, and the name symbolizes that we can use multiple infrastructure as a service frameworks. It symbolizes that we can federate a number of resources in academia and industry. We've given here just a couple of examples. It symbolizes that we can assist in the deployment of services in the entire software stack that is relevant for big data analysis, naturally also other areas. Then Cloudmesh exposes hypervisor-based and bare metal provisioning to the user. This means when you have an infrastructure as a service, it could be, for example, having different hypervisors. You could be then testing out different architectures based on different hypervisors. So would you want to test out Docker? Would you want to test out QEMU? Would you like to test out other software in this regards? Yes, the goal of Cloudmesh is to expose these toolkits to the user. Naturally, because this is such a rich area, we need to have also a rich interface to these services. Certainly we want to have a command line, a command shell, APIs, and a web interface. As already previously mentioned, a lot of the requirements came originally from FutureGrid, but FutureGrid also contributes certain features to Cloudmesh, such as, for example, the metric framework that has been developed, the repeatable experiments that have been prototyped by FutureGrid and pioneered by it, multiple infrastructure as a service framework support, and most importantly, the mixed operation model, where standard production cloud is being provided, as well as a cloud that allows experimenting with the software to expand upon this. The functionality requirements that we have identified for Cloudmesh, I repeat once more, we have already mostly listed a multi-cloud environment, but here we need to be stressing that we also need to be expanding the clouds. That means if a new cloud comes available, we need to be able to easily integrate it. We need to be able to integrate external clouds, public clouds, and my own cloud. Multi-provider resources and services must be enabled. We also must enable raining of operating systems, services, platforms, and infrastructure as a service. Often, people don't use the term rain, but they use provisioning, which is maybe the more academic term. We are using the term rain because it has a little bit more of a meaning, because provisioning sometimes is only being meant to deal with the operating system. However, what we try to do is we try to put the operating system, we try to put the infrastructure of the service, we try to put the platform as a service, as well as the software services onto the resources. Thus, because we are addressing the entire software stack, we use the term rain in order to avoid the exclusion of the other infrastructure as a service and software as a service provisioning features that we want to provide to the user. Naturally, we want to also provide monitoring and the reproducibility of experiments. So how does this raining look like? Well, we are in the cloud, so let's put a cloud up. Well, we want to rain something on top of our resources. So how would that look like? Well, we would like to rain a virtual cluster maybe on the resources, a Hadoop cluster, an operating system image, or virtual machines. So we are addressing here software as a service, we are addressing platform as a service, we are addressing the operating system, we are addressing the virtual machines as part of infrastructure as a service, and naturally others such as, for example, as we previously mentioned, Mahout and other software services. This is being managed through a template repository, so that you can rain those particular services on a multitude of resources and not just one resource. The functionality is a central part of Cloudmesh, which can be expanded through multiple components. And at this time, we have focused on information services, provisioning management explicitly through rain, however also cloud shifting and cloud bursting, which we will be going into a little bit later, virtual machine management, experiment management through a shell and IPython, as well as accounting integration, such as, for example, integration of an LDAP server or integration with Exceed, which we have previously demonstrated nicely via Cloudmesh or other resources. The usability requirements that we have are related to our command line tools, the web portal, and the Python API. Naturally, the toolkit must be open source, extensible, easily deployable, and documented. Here's an example of the user interface to Cloudmesh. You may have seen this in other presentations already, but it provides a fairly straightforward interface to virtual machine management and HPC cloud batch queues. Here's a more close-up picture of the machine management. Here we see a multitude of clouds, and therefore our federated idea of exposing all the available resources to the users. If you typically use OpenStack, it may just show you OpenStack, but here you can see, for example, Azure is integrated. Azure is not OpenStack, but yet the look and feel of managing virtual machines in Azure is the same as you would be managing OpenStack virtual machines. We have a plus button integrated, so when you want to create a new virtual machine, you just press the plus button. Defaults are used for you, so if you want to repeat and want to have additional virtual machines, you just press the plus button. So there's no need for complicated menu for starting up repeated virtual machines. We have an image selector for each of the virtual machine infrastructures, and we have a flavor selector for the infrastructure as a service. And these will become the defaults so that you can, when you press the plus button, these are being taken as defaults. We have a nice command shell. Actually, this is one of our very successful projects. We get multiple, in the order of 100 to 200 downloads a day on our toolkit that is called CMD3 that we use in order to write the Cloudmesh shell. This allows us to specify fairly easily extensible commands and expose the more detailed Python API through a command shell. Those that are familiar with MATLAB may be knowing a shell. It's similar like this. You can see our demos of this. Furthermore, we have also integrated this into IPython. Naturally, this is somewhat coming for free because we have our tool developed in Python itself. What we are currently doing is we are improving upon the functionality so that it's easy to use for the user. And you can already see an example in this IPython notebook. So when the user comes in, he could be using IPython notebooks to create repeatable experiments so that he can be sharing them with other users. The monitoring is being worked on. We have, for example, here a demonstration of listing the service architecture of our clusters. Here we display which services are being running right now. This includes HPC services, OpenStack services, and several other services. The right upper image shows the temperature measurement, and the picture to the lower left shows how the services are distributed by numbers in the histogram. The architecture of Cloudmesh has three main levels. The management framework that allows us to federate resources to conduct system monitoring and provides the access via the user. We have internal services that are dealing with provisioning and execution. That means we can conduct platform as a service provisioning and federation, infrastructure as a service, and compute provisioning. We have security built in, and the lowest level is our resource level so that we can obtain a view of like a federated resource infrastructure. Not everything is completed yet, and we are working towards adding new components If you have a good idea for a component that you would like to add, let us know and you can contribute it. The building blocks that we currently have includes the inconvenient abstractions of, for example, bare metal provisioning, as well as the infrastructure as a services. Internally, we use, for example, also libcloud and Cobbler. libcloud for infrastructure as a service, Cobbler for bare metal provisioning. However, the interface with OpenStack is done directly via REST calls. And this avoids that we create a dependency on libcloud. And we had in previous incarnations of our software real problems with libcloud because it did not give us the necessary information that we really needed in order to develop advanced cyber infrastructure services based on infrastructure as a service frameworks such as OpenStack. So what we do is we provide the entire information that is being provided to OpenStack by, for example, an infrastructure as a service query command. We have an interface to OpenPBS while we can view, for example, clouds. It would be easy to extend this with other more additional functionalities, but this is not where we are currently focusing on. User management has previously done via Exceed in some editions and FutureGrid. We would like to replace our user management with our Python-based user management. We are naturally using AMPQ, RabbitMQ, and Celery. We are in the process of integrating Slurm and Chef. We would also be targeting OCCI as a compatibility library, but this is not necessary at this time, so we will probably just focus on some bare metal integration, in which we try to conduct. One of our ideas is also, for example, to look into Foreman or alternative bare metal provisioners to Cobbler. OpenStack Ironic comes in mind most prominently. So the provisioning and execution framework that we have as part of our RAIN includes bare metal provisioning, virtual machine provisioning, and in future also network provisioning. We want to also address storage provisioning and make sure that platforms, infrastructure, and federated provisioning is possible. That means sometimes you just assume a platform as a service is already deployed. What we would really like to do is here a couple of resources, invoke this particular service, and then an infrastructure as a service framework is being deployed on it. Resource shifting is very important as part of the academic community. One of the problems we have, in contrast to, for example, organizations such as Google or Amazon, which seem to have virtually unlimited resources, unlimited in quotes. At the university level, resources are very scarce, and we want to share them naturally and want to utilize them. But we often observe that maybe one day the resources are not that well used, while at the other day they are very well used. So while a user may be wanting to run HPC job one day, he may want to also explore cloud computing the other. I assume you have a roster in a university that teaches MPI as well as cloud computing, and you have just one cluster. How do you do this? Well, we can shift resources between these services and can make sure that some resources are being associated dynamically to the appropriate need. Let us demonstrate this with this simple highlighted graphic. Here we have three services: OpenStack, HPC, and Eucalyptus. And we have an autonomous runtime service that is going to be planned to be implemented. And we, for example, find out now what our scheduler needs to do in order to do resource shifting between resources. Maybe we find out that OpenStack is no longer used that much, but our HPC demand has become larger. that means we need to be figuring out how to move resources from our HPC, from our OpenStack cloud into the HPC services. What we do is we reprovision the operating system on the particular resource that is no longer being used, and put a new operating system on it that contains the HPC services so that it can back register onto the HPC. Well, the reason why we want to have a different operating system on there, we want to make sure that the system is clean and no additional potentially malicious software is being left over onto the service. Resource federation is certainly really important for us in Cloudmesh, because we would like not only to submit jobs to OpenStack, but also Azure and others. So we have enabled that. The status is right now that Cloudmesh has been released with the focus on developing 3 of its components. This includes virtual machine management in multi-cloud environments, cloud metrics in multi-clouds, which we have already demonstrated that this works, and bare metal provisioning. The bare metal provisioning is still somewhat in prototype state. We need to be doing a little bit more on our security side. Cloudmesh has successfully demonstrated in FutureGrid and will continue to be evolving as part of future systems. And we have also demonstrated this as a hosted service. Right now, we prefer that users are using it locally. A REST interface to management functionality is under development. And I have to mention that Cloudmesh is an open source project that uses mostly Python and JavaScript. And we are very open to collaboration, so if you would like to join the team, please contact me and we can discuss this. The conclusion is that we also have identified that it's very convenient to have a software developed distributed system, software-defined distributed system toolkit, so that we can support even internally our needs for setting up new experimental environments that may be more suitable or performance goal-oriented, in contrast to just having a single operating system or just having a single cloud in our environment. Cloudmesh metrics have proven to be very valuable. The statistics that you saw at the beginning are an attest to this. Such insight hasn't been shown by other projects. Our project has clearly shown that. With that, I would like to thank you for your attention, and I would like to encourage you to read other things about Cloudmesh. Thank you very much.